Good. So good afternoon, everybody. It's really a pleasure to see so many people here for another IQOQI Colloquium. This is the 8th edition. As you might remember, we used to organize an IQOQI Colloquium, one in the fall and one in the spring, so two per year. Last one was in the fall of 2019 with Jack Harris, and of course we had to do a break because of the pandemic. So it's really good that we can have this again, and that we have today Eugene. So let me make a brief introduction to Eugene. So Eugene Demler did his degree in physics at the Moscow Institute of Physics and Technology, and then he moved to Stanford to do a PhD. He got his PhD in 1998 with Professor Suchan Zhang, and then he moved as a postdoc to Santa Barbara, to the Institute for Theoretical Physics for a couple of years. And then he moved to Harvard in 1999, first as a junior fellow, then as an assistant professor from 2001 and 2004 to become a professor of physics in 2005. And only recently, a couple of years ago, in 2021, Eugene accepted an offer from ETH Zurich to be a professor of theoretical condensed matter physics. So Eugene is a theoretical physicist, a condensed matter physicist, and together with his group, he's very interested in the developing of general theoretical tools for the understanding of the effects of interactions and establishing a common framework for the understanding of the physics of strongly correlated systems. So his research is very broad, and he's very interested in many different systems, from high temperature superconductors, heavy fermion and organic superconductors, quantum Hall systems, quantum antiferromagnets, mesoscopic superconductors, and also very interested in understanding of the effect of dissipation in quantum phase transitions, and also Bose-Einstein condensation of alkali atoms. So maybe more close to IQOQI, of course, we all know his seminal contributions in quantum simulation with ultracold atoms, in optical lattices, both in theoretical proposals, but also collaboration with experiments. Also his work on many-body dynamics in closed systems and how they thermalize, as well as quite recently now more works on strongly QED, so strongly light matter interactions. So of course, all this research has been awarded with many honors, and it's always difficult to summarize, so we'll just pick up a few of them. So for instance, recently he got the Hamburg Prize for Theoretical Physics in 2021, also the Simons Investigator Award, and he was also elected as a fellow in APS at 2012, and in 2015 he was also elected as a distinguished scholar at Max Planck Institute for Quantum Optics. So it's of course a big pleasure to have Eugene here during these days with us in Innsbruck, and to have now a colloquium from you. So we look very much forward to the talk. So thank you, Eugene, for coming, and we'll look forward to your talk. Thank you.
Thank you, Ariel, for this very kind and generous introduction. Great, thank you. So yeah, I really enjoy and hope to continue. Look forward to sort of maybe half an hour more after my talk of very stimulating discussions. It has been a pleasure, and I appreciate the opportunity to come. I'll tell you about the work that we have been doing, and I want to begin by sort of acknowledging people who really did the work, who should take the credit. So this is Annabelle Bort, who is now a postdoc at ITAM, Fabian Grust, who was a postdoc at Harvard before starting his group at LMU, Dries Sals, who also was a postdoc at Harvard and now has his own group at NYU, and Kushal Sitaram, who was kind of interestingly, who was a graduate student in my group when he was an MIT student, and now moved as a postdoc to Harvard after I left. And what made this work particularly exciting is the opportunity to interact and collaborate with experimental colleagues, and especially with the groups of Emmanuel, Marcus, Chris, and Mark, and I'll sort of explicitly discuss kind of joint project as we go along. So let me start with an introduction. I think in the last 2 years it was hard to avoid discussion of all the promise of quantum computing. At least I still consider myself to be a bit of an outsider, and I really like the comparison given by Serge Haroche that this is a field trapped between hype and hope. And some of the early projections were quite remarkable. So the so-called Rose's law, which predicted that, well, okay, a few years ago, we should have had quantum computers which had more computational power than the universe. And even more recently, Hartmut Neven introduced his law according to which the computational power of quantum computers should scale double as exponential and exponential, just because the number of qubits will scale exponentially and Hilbert space is exponential in the number of qubits. And that is not just an academic pursuit of, obviously it is having kind of it's being supported by now industry with a lot of sort of considerable investments. And actually I had a remarkable visit to the IQT. It was kind of amazing what can be done now. But I think many of us will agree that if we look at what's happening today, like in the famous Gartner cycle, we're probably somewhere near the peak of inflated expectations. Probably there will be some disillusionment coming. And I think, and in fact, I would say some of it is already coming. Some of sort of the theorists start talking about sort of hype being even a problem in the field. But I think what will really matter in the long run, and in the not such a long run, is what will be the real contribution from this kind of quantum technology on things that matter for science and society as a whole. And one of the important ideas on this was given by John Praskill, who suggested that what we should focus on is not really perfect quantum computers with millions of qubits, but rather on the NISQ technology when we have limited number of qubits and that have a limited number of operations available to them. And then sort of in a different venue when he was predicting, so when sort of what are the fields where quantum computers can actually be useful, he suggested that he doesn't yet see any evidence and that they will be useful for solving problems which are intrinsically classical, but that they should have a bigger impact on problems which sort of are quantum in character. And then there is this interesting Twitter which sort of rates different statements in the quantum field on bullshit and not bullshit. So this was qualified as a not bullshit statement, which is a high praise. And today I'll try to sort of discuss one of these applications which I think well, we can expect this technology to have an impact, and I'll try to argue that in some areas we already see this impact, and this is the area of quantum simulation. And this idea, of course, goes back to Feynman, who talked about like an idea that if we have a quantum problem that's very difficult to solve, then we can try to reproduce it in a different system, sort of maybe a scaled down version, and get some insight into the problems that we want to solve. And at least to me, I think the kind of modern era of this quantum simulation started with the paper by Peter, when they suggested that one can use cold atoms and optical lattices to simulate a problem that sort of people from condensed matter background like myself have been thinking about, and this is bosons in a lattice with local repulsive interactions. So the type of quantum simulations that I will focus on and that have been extremely popular sort of in different areas of research have to do with trying to understand high TC recuperates. I'll not go through all of the details, but just to point out that even though it's a complicated chemical compound, but the essential electronic physics is believed by many people to be analogous to a system where we just have fermions moving in a periodic lattice. This periodic lattice can be created using standing waves of using laser beams and with some local repulsion. So obviously we have sort of strong rescaling of energy. So we talk from like whereas in the electronic system we talk about energies of hundreds and thousands of Kelvin. Here we talk about sub-micro Kelvin, but that is just another manifestation of universality of physics, that we can sort of study similar phenomena, even though we're looking at very different energy scales. And what will be the emphasis of my talk is the kind of, you can say, technological development that was started a few years ago, and this comes from quantum gas microscopes. It's the idea that now our experimental friends can actually measure every particle in a many-body state. So if you look at this, so this is not a theorist representation of sort of a state of fermions in a lattice, but these are results of actual experiments taken from the Munich group. So you can see that where you see the red dot, so this is spin-down fermion, a blue dot is spin-up, or let's say the empty circles where there are no fermions. So sometimes in a kind of joking manner, I compare this to the style of art known as pointillism, which was a type of impressionist art, which instead of using sort of these brush strokes, relied on individual dots, which together added up to beautiful paintings. So what we will be discussing today is how to take this picture composed of dots, which tells us something about the many-body state, underlying many-body state, and what information we can extract from such pointillist many-body paintings. And it's not surprising that when we look at if the result of experiments are now pictures which sort of contain a lot of information, that it's actually beneficial to start using tools of classical machine learning in order to analyze information contained in these images. Okay, so this is the outline of my talk. So I'll first talk about sort of simulation of the Fermi Hubbard model using optical lattices, and I'll sort of focus in the beginning on trying to understand a long-standing problem of magnetic polarons, how, let's say, dopants move in the magnetic environment, then how they actually how we go from a liquid of these polarons to from a liquid-like behavior, and also tell you about the first experimental observation of magnetically mediated pairing in the Fermi Hubbard type model. Then I'll also sort of say a few words how one can use tools of machine learning to analyze the snapshots of many-body states. And then in the second part of my talk, I will shift gears and try to discuss a subject, how quantum simulations, I think, can start moving outside of the domain of sort of pure physics, but sort of start addressing questions which are relevant to a broader community. In particular, I'll talk about using simulations to study, to do NMR inference, which is very important for biomedical research, and we'll talk about, let's say, the first experimental demonstration of computation of NMR type spectrum on a quantum computer. Okay, so but let me begin by talking about Fermi Hubbard model, magnetic polarons. And when you hear polarons, probably most of you recall this sort of the historical picture that they were first introduced when Landau thought about electrons moving through a lattice and distorting distorting the crystal structure around this electron. But these days we think about polaronic effects more broadly. So for example, when we talk about sort of magnetic systems, we can think about electrons, like mobile electrons, as dressed in some kind of magnetization cloud, or even superconductivity can be understood as polaronic effect. The first electron creates a distortion of the lattice, which then attracts the second electron. And these are examples of what is called bosopolarons, namely we have a quantum particle which interacts with bosonic degrees of freedom, such as, let's say, phonons in this case, or magnons. But there are also important problems which have to do with the Fermi polarons, such as when an impurity spin interacts with the conduction electron. So now the bath is the fermions. And of course, so here there was a lot of beautiful work on Fermi polarons done in Rudy Grimm's group, when, let's say, they would inject fermionic impurity in a strongly interacting state, also in the fermionic bath. Okay, so so we sort of defined the general idea of the polaron. Now, in terms of Fermi Hubbard model, I it would require a full course to just explain all of the features. So I just want to bring one aspect for non-experts that will be important for our discussion. And this is the idea that when we have very strong interactions, a very strong on-site repulsion of fermions, then this favors antiferromagnetic correlations between fermions. You can think about it from the simple argument that when two fermions on neighboring sites, if they have opposite spin, then one of the electrons can gain at least some kinetic energy by going to the into a state with double occupancy and then coming back. And therefore, energy can be lowered by this virtual tunneling, whereas for parallel spins, of course, Pauli principle does not forbid such tunneling. And therefore, one can encode this tendency towards anti-aligned spins in the form of this antiferromagnetic Heisenberg-type interaction, which can be related to parameters of the lattice single particle tunneling and repulsion. So when I will show you theoretical work done on sort of simulations of the Fermi Hubbard model, I'll switch from kind of the original Fermi Hubbard model and sometimes show so-called TJ model, which is a very close, basically derivative. You can see that it keeps its this nearest neighbor antiferromagnetic interactions, but removes the high energy double occupied states. Okay. Now let's talk about how Polarons emerge in the Fermi Hubbard model. So we begin in a state in which, imagine on every side we have a fermions, and we said, well, the system favors anti-aligned spin, so we start with this sort of perfect checkerboard. But now we remove one of the electrons, right? And then we let, and that's what sometimes is called creating a hole. Now we let this hole to move, and it moves, and notice that it does something quite remarkable. It actually changes spin configuration, right? To begin with, all bonds were antiferromagnetic. Now some of the bonds became ferromagnetic, which means we introduced magnetic frustration. So one can think about it that if, so the site where, in a sense, the motion of the hole started is by analogy with 1D, often called spin, and whereas the site where the hole is at a given point is called holon. And you can see that there is kind of a linear change in magnetic energy as spin and a holon separate from each other. And this motivated many people in the very early days of sort of high TC to suggest that we can think about dynamics of holes doped into the antiferromagnetic Hubbard model by analogy with QCD. We know that in QCD we have mesons which consist of pairs of quarks with a linear potential between them. And here we can see that in like very similar structure emerges indeed if we try to analyze sort of the interplay of the charge motion with magnetic degrees of freedom. So, okay, but now let's look at what experiments tell us. So these are results from Emmanuel Bloch's group. So here they looked at the motion not of a hole but a doublon, but it turns out that for the Fermi Hubbard model, this is exactly the same. So it's a system in which there is just one doublon in this plane, and this doublon can move anywhere. However, what we're interested in is how magnetic correlations are affected in the vicinity of the doublon, and therefore what they do is when presenting the data, they always show magnetic correlations, the change in magnetic relations relative to the position of the doublon. So physically, this should be thought of as a three-point correlation function, because we correlate where the doublon is with correlations between the two spins. But again, emphasize, even though we always put, like in these images, we always put doublons in the center, but in reality, in this experiment, doublons was actually free to roam through this entire plane. And it's just we really want to be in the reference frame of the doublon in order to see how correlations change. And if we focus on some of the most dramatic changes, let's look the diagonal correlation. So far away from the doublon, the red, which means ferromagnetic. And that's indeed what you expect, you know, this undisturbed antiferromagnet. On the diagonal, we have spins pointing in the opposite direction. But now, if we look at what's happening next to the doublon, you see that even the sign of the correlations has been altered. So somehow the motion of the doublon was sort of really led to dramatic modification. And sort of qualitatively, it's actually not so hard to understand this. So let's start with this picture of the hole before it started moving, you notice these two fermions, they are nearest neighbor, and therefore they're antiferromagnetically correlated. But now this hole moves, and the same pair of fermions is now on the diagonal. And so now when we average spin correlations on the diagonal near the doublet, you see that we're actually including some of the spin correlations which used to be nearest neighbor, and therefore they remain antiferromagnetic. On the other hand, we still have correlations which were inherited sort of from the state before the hole was moving, and it's ferromagnetic. And so now we have to sum over them, but actually to begin with, nearest neighbor correlations are stronger. And that's why when we sum, we actually find that the net spin correlations are antiferromagnetic on the diagonal surrounding a doublet. And one can actually do this sort of advance this idea further by developing full variational wave function motivated by this mesonic picture, by saying, well, okay, let me basically solve the following problem. If I want to understand the motion of a hole, it is like it's like a particle moving in the presence of a linear potential. And the main change is that the nature of the lattice is modified, because when when the hole moves, it actually matters which trajectory it chooses, right? Like usually if you think about single particle physics, all the instantaneous states can be characterized by where the hole is. But now, actually, depending on how the hole went, there will be a different string left behind. And therefore, the lattice on which we need to analyze the whole motion should be thought of as more of a beta lattice configuration. But otherwise, it's like tight binding model. We know the string tension, which we can actually extract by knowing spin correlation functions that have filling sort of in the undoped case. And then once we know the wave function of the hole, we can compute how the motion of this hole will reshuffle the spins, right? Because basically, as we said, as a hole moves around, it actually reshuffles spins, move them to different sublattice, and that's something we can do quantitatively. So this is what Fabian and Nabal have done, and now you can see that. Okay, let's just look at the data corresponding to the moving hole. On the left, you see experiment. And that is, again, it's the sort of now, in this case, these correlations of nearest neighbor spin correlation as a function of distance to the doublet. And again, that's what we see before, that they stay antiferromagnetic, but they're somewhat reduced near the doublet. And the theory is an excellent, this sort of geometrical string-like mode with an excellent agreement with experiments. And here we're looking at diagonal correlations also as a function of the distance to the doublet. And we saw that how it changes sign. It's ferromagnetic away from the doublet, becomes antiferromagnetic close to the doublet. And again, this geometrical string model actually captures all of this behavior. And let's say in zero, well, of course, theorists want to do to have something at zero temperature. Fortunately, experiments have to be done at finite temperature, but we can do something like DMRG on finite cylinders and check how this geometrical string model of magnetic polarons works on the cylinders. And again, you can see excellent agreement between theory and this sort of this phenomenological string theory model and full DMRG. Okay, but our colleagues became more ambitious. So this is, I'll now discuss kind of an experiment done in Marcus Greiner's group, and the lead people on this were Christy Chu from Marcus's group and Annabelle Bort. So they decided to look for the strings, right? We said that the key, the key element of this magnetic polaron is the idea that as a hole moves, it leaves behind the strings. So the question they decided to ask, let's take images and let's ask, can we actually identify strings? So how does it work? Okay, so this was our microscopic state. And maybe before I sort of jump into describing experiments, let me make one sort of clarification. At that point in Marcus's experiment, they could not sort of instantaneously image spin up and spin down fermions. They had so previous data I showed you were from the group of Emmanuel Bloch. So in Marcus's group, they had lower temperature, but unfortunately, they had to decide whether they image spin up or spin down fermions. So, but as you'll see it's not a showstopper. So let's say they decided to measure the blue fermions. Then, okay, so when they measure, they only measure sites which have exactly one blue fermion, and then they compare it to the sort of classical checkerboard configuration. And then they see that the difference, and then they mark all the sites where they see the difference, and they see, well, there is a segment of length 4, right? And then there is two segments of length 2 and one sort of single site. So then they sort of show a histogram, like so. From this specific image, they see a string of length 4, 2 strings of length 2, and 1 string of length 1. And then they sort of one can analyze a lot of these snapshots, right, and extract distribution function of the strings. And you can see that, so actually, sorry, I think I should have, nope, sorry. Thought I have bad animation, but if you look at plots at the bottom, a dot at the bottom, so these actually strings at half filling before one actually even introduces holes. And then when one introduces hole, the probability to find strings increases. And it may not look like a lot, but notice that the vertical scale is actually logarithmic. So for longest strings, the probability to find longest strings due to doping goes up by almost an order of magnitude. Therefore, it's a dramatic effect. And you could ask, oh, maybe it's just because, you know, we removed some spins, and that sort of obviously generates some kind of longer strings. But you see that if we were to take you know, the undoped system and just randomly sort of remove some of the sites corresponding to the hole, the increase in the number of strings would be very marginal. It's this golden dashed line. So that's why you can see that in order to actually account for this dramatic increase in the number of strings, we actually have to take into account this sort of the effect that the hole motion has on spin configurations. Okay. So we sort of understand aspects of what's happening to a single hole, but obviously what's interesting to us is what happens to how that, when we have many holes, how do we get an interesting many-body state? And in particular, there are many puzzles about cuprate, but there is one curious puzzle, and this is that if we sort of want to recognize the kind of properties which look like familiar metals, it turns out that it has to be a regime of the so-called strong doping, that basically we have to remove many holes starting from you know, this state with one fermion per site. Whereas when we come to smaller doping, actually many properties look strange. In particular, so there is this canonical property which basically asks, well, if I let's say, how do my quasi-particles look? Do they look more like free fermions or not? In Fermi liquid, with lowering the temperature, they should look more and more like free fermions. And that's what happens on the overdoped side. But on the underdoped side, it's actually the other way. So there is this very kind of important crossover, right, from one type of behavior for underdoped regime to a different type of behavior in the overdoped regime. And so I'll try to convince you that we now see the same crossover from these cold atom simulators, and we can understand its nature. So, right, and so this is, again, data from the Munich group, and I'll not talk about all the data, but I'll focus on just some. So they now, let's say, they look at two-side correlators. So again, it's something sort of what, for example, would be related to what one measures in neutron scattering. But now let's focus on two fermion correlators, which in the antiferromagnetic state correspond to ferromagnetic coordinations, say like these two on the diagonal, or let's say in this case, this would be second nearest neighbor on the horizontal. And what's shown is how these correlations evolve with doping. So here you see that they start being ferromagnetic and then they change sign. Again, they sort of start ferromagnetic and then they change sign. And in fact, if you, all of this change of sign actually occurs around 30% doping. You can go to longer range correlation and still 30%. And why at larger doping all correlations become antiferromagnetic, we actually understand quite well. It's, remember, like from your basic Fermi liquid theory, if you take two fermions, then fermions with the same spin, they have Pauli principle. They're unlikely to come close to each other. Therefore, we are much more likely to find fermions with the opposite spin. So therefore, at larger doping, indeed, we find this sort of spin correlation as we would expect in the Fermi liquid, whereas at smaller doping, they behave as we would expect in an antiferromagnetic state. And then one can convert these correlations computed in real space to correlations in momentum space. And this is, say, what would be measured in neutron scattering in solid state materials. And if one, so in the antiferromagnetic mode state, we have this peak at pi pi. That's the hallmark of the antiferromagnetic state. Then if we take weakly interacting fermions, if one does just band structure calculations, so weakly interacting fermions, one predicts what's called incommensurate structure, kind of peaks split away from pi pi. So we see that as one changes doping, one actually, there is kind of a change in behavior from these antiferromagnetic type correlations, which are peaked at pi pi, to incommensurate up correlation, which we would expect from weakly interacting fermions, again around this 30% doping. And okay, maybe I'll just then focus on this. So this is now something that is again special to cold atoms. This is now like 3-point correlation function, what we discussed before. This is like 2-spin correlation function as a condition on how far they are from the hole. And you can see that close to half filling, that's basically like one hole in an antiferromagnet. That's what we discussed before, and the hole induces all correlations which are opposite to what they were without the hole, right? So for example, nearest neighbor without the hole were antiferromagnetic. Now, because of the hole, they acquire ferromagnetic correlations. But for larger doping, you see that all correlations simply become antiferromagnetic. So even in this high order correlation function, again, we see this transition from something that's well described from the picture of magnetic polarons to something that's well described from the Fermi liquid picture. And one can be, let's say, quantitative. One can ask, okay, so this experimentally measured 3-point correlation function. Let's compare to, let's say, free fermion theory or to some kind of models, sort of mean field theories, such as RVB theory, and you find that they all work at higher doping. Then if we take string theory, well, string theory works at small doping, but none of the theories, but say string theory does not work very well for large doping, whereas this, let's say, this pi flux or approximation of weakly interacting fermions do not work for small doping. So clearly we have a crossover from this Polaron type behavior at small doping to the Fermi liquid type behavior at larger doping. Okay, so I think that sort of gives us strong evidence that indeed, like this crossover observed in the cuprates sort of corresponds to a change from this Polaronic liquid type nature of the state to the Fermi liquid type state. Okay, but then of course the question is, how do we see pairing? And so let me give you an idea that actually Annabelle and Fabian came up with, and that was then implemented in experiments by Emmanuel. So roughly the idea is as follows. Well, if we take something, okay, sort of simplify and bring it, so in some sense not in the way it was historically occurred, but just to shorten the discussion. Think about a system such as a ladder. So in a ladder, we actually, okay, if we think about transverse spin interactions, sort of antiferromagnetic exchange, we know that we want to have singlets. And then if you imagine if you introduce sort of holes like you dope, well, it would be beneficial for these holes to be on the same rung so that they sort of break the least number of the singlets. Okay, so it's kind of good from the point of view of magnetic interaction between the chains. But then you realize, well, but what opposes this is simply kinetic energy of the holes, right? Because if they are on the same rung, they can no longer move. Whereas if they were on different chains, you know, this hole can now hop to the other chain and back. So therefore, clearly, kinetic energy of individual holes actually would favor holes moving away from each other. So if we want to enhance pairing, then it would be natural to enhance exchange interaction between the chains and suppress tunneling between the chains. And like sort of from the point of view of traditional solid-state physics, this just doesn't make sense because we know that this transverse J prop is like tunneling squared. But then one can use the unique trick of the cold atoms, and this is the idea that we can make metastable states. And in particular, the idea is that one can apply a bias voltage. And so if one applies sufficiently large bias voltage between the chains, if it's large enough, then actually single particle tunneling is suppressed. And therefore, we will actually prevent individual holes from moving. On the other hand, virtual tunneling is still allowed, and in fact, it's even now cheaper because now, let's say, this fermion can go into the kind of chain at a lower potential, and this the energy cost of this double occupied state will no longer be U, but it will be U minus delta. Right? Therefore, by applying this bias between the chains, we can suppress single particle tunneling and enhance interchain magnetic interactions. And this is exactly what was realized in experiments in Munich. And so here you can see a snapshot. So this is spin unresolved, but you can obviously see, okay, so here we have two fermions on the same rung, and now here we have two holes, and holes are next to each other. You can say, oh, maybe it was like, result of searching through many images just to find the correct one. But no, this is actually like quantitative analysis. So what this shows is correlation function between holes in different chains. And you can see it for two cases. One is without this bias. So this is kind of plain vanilla Hubbard ladder. You can see that we actually have suppression in the probability to find two holes on the same rung in the simple Hubbard ladder. And that's what we said. Oh, kinetic energy of individual particles actually does not favor this tendency. But when the strong bias was added, like it was half of the repulsive U, we actually clearly see a very strong increase, like very clear tendency of the holes to bunch. So we really see that that now sort of holes do not want to separate. And you can also easily understand it from these images, right? So if, let's see, if we start with now a hole pair like this, and this hole moves around, then, like configuration which used to be singlet on the rungs, now they they're sort of spread out between different rungs, and so a system can no longer benefit from the singlet configuration, and therefore this sort of sacrifices this large transverse exchange energy. So it's really this magnetic interaction which now keeps the two holes together. And there are still interesting questions which hopefully will be answered in future experiments because when they unfortunately, systems are too small, so we don't yet know what happens when they add many hole pairs. Like when they added two hole pairs, they see that they try to stay with sort of far away from each other, or like three hole pairs, again, they try to stay far away from each other. But whether they will, like if we really take a large system, whether this will be a kind of a superfluid of such hole pairs, or it will be a crystal that this repulsion will be too strong, I think hopefully will be answered in future experiments. Okay, so and then let me also we said, okay, we have a lot of images, so how can we use machine learning tools? And so one of the approaches that Annabelle really tried was to say, well, if machine learning is good in separating different types of images, let's ask it to separate different types of theories. And so we can take two competing theories. There is one, this pi flux RB theory. Details are not important. Just what's important to us is that it's kind of a theoretical approach which is mean field, which says, oh, when we dope holes, we suppress magnetic correlations, but they are suppressed kind of on the average, right? It doesn't really take into account this locality of magnetic correlation suppression in the vicinity of holes. And then we have this geometrical string which really says, oh, if we start with holes, and like a hole really reshuffles magnetic correlation in the vicinity of itself. And then one can take neural networks, and let's say we have three ways of generating images. So we have two theories, and the third one is experiment. And we can do different tests. So, for example, one can train on just like these three theories and ask, are the neural networks then sort of very comfortable sort of distinguishing these three approaches? And what you find is that the pi flux can always be easily distinguished. However, these neural networks are very confused about geometrical string models and experiments, which shows that geometrical string actually model gives us sort of snapshots which are very close to experiments. Or another way was to train another neural network just on these two theoretical models without showing any experiments, but then give experimental data and then ask to assign this experimental data to one of the theories. And you see that, again, until sort of small doping, essentially the system gives dominant assignment of experiments to geometrical string rather than pi flux. And you may be confusing, oh, it's like very weak preference, but you see that this is kind of preference based on a single snapshot, which has kind of limited information. Like say at most, it would be 8 by 8. If you give a few snapshots already, then this 15% difference immediately goes to sort of almost 100%. Okay, but this is kind of like a black box. And so one, of course, would like to understand how what were the criteria, how those neural networks actually distinguished different theories, for example. And so this is where sort of we basically, this was kind of the idea really taken over by Una Kim with her group and also Annabelle. And they designed, like, just changed the nature of neural networks. Again, I'll not go through the details for the lack of time, but you can. But this allowed them to really understand. So, what were the features that actually the neural networks recognized? Like, what was this 2-point correlation, 3-point? And what they understood was that it was really 4-point correlation function that was used to identify like specific theory. And actually, the motifs which we see in this four-side patterns are the ones that we can understand very easily. Like notice that this on the diagonal we have antiferromagnetically correlated spin. So this is what happens when the hole moves. Or here again, as a result of the hole motion, like maybe hole motion in this direction, our nearest neighbors we see not antiferromagnetically aligned spin, but ferromagnetically aligned spins. Okay. But now let me change gears. So far, I think it's this is kind of a very kind of remarkable stage in quantum simulations of Fermi Hubbard model, and we're learning a lot about it's a different perspective on this model of strongly correlated system than traditional solid-state physics experiments. But you can say that, well, does it really have an impact on the kind of community, on the broader community? And in fact, maybe one can ask that, okay, we have this wonderful quantum simulation, and but you know, it's really more kind of, it's too focused on physics problem. Of course, sort of beautiful experiments done here in collaboration between Rainer and Peter's groups, experiments on sort of modeling water molecules or a demonstration of quantum supremacy, but it's not something that ordinary people can relate to. So what we wanted to do, actually this was a challenge brought to us by our colleagues from Harvard Medical School, is to use quantum simulation that would be of interest in biomedical research. And the specific problem that they brought to us was the question of NMR inference. So in a nutshell, the idea is that, okay, they want to identify chemicals that are present like in the human body, and NMR is one of the powerful techniques, but the kind of information that it gives us is sort of the spectrum, NMR spectrum. So we want to go from the spectrum to the molecule, and they said that at least as a first step, what would really help them is to know the Hamiltonian, because Hamiltonian contains information about, say, symmetries of the molecule. So like, to reduce it to the physics problem, what we have to do is we have to understand which Hamiltonian has a correlation function computed at infinite temperature that matches, you know, what has been measured in NMR experiments. And the fact that this is infinite temperature is very important. Well, it has to be infinite temperature because if you take an NMR spectrum on a kind of living tissue, you have to keep this tissue alive. and the energy scale of NMR are orders of magnitude lower than energy scale of, let's say, Zeeman energy or interaction between these nuclear spins. So therefore, if you think about it naively, you really have to compute this spectral function over the entire Hilbert space, which we know is exponentially large. So, okay, and just to give you an idea, again, where just like even like what we started with, it's probably like it's the simplest version of NMR. And colleagues from classical NMR tell us, oh, that's probably not going to be a kind of killer application, because that's what they can believe they can make a lot of progress with their traditional methods. And this is the field of metabolomics, basically how from the spectrum of kind of NMR spectrum of small molecules to identify this metabolites. And this is something that they need to understand, okay, basically how like people I don't know, process sugar, coffee, like you can recognize coffee and how it breaks on metabolites. But anyway, what's important is that at this moment, people sort of have this, like in biomedical sciences, they talk about dark matter. So dark matter is not only what physicists try to solve, but also what people in biomedical sciences are trying to solve, that they have many types of spectra which still have not been identified. And even smaller fractions is being used in experiments. But in reality, I will, okay, so if you push me, I will admit that probably like this, okay, I'll discuss why these kind of NMR spectra in liquids are particularly simple, that in order to look at harder problem, we probably have to take like molecules which have dipolar interactions, or we have to talk about problems which require averaging over, say, orientations, such as, let's so-called powder NMR. So it's a big field, and there are many interesting questions, but I will, just for demonstration purposes, I'll talk only about a very simple version of it. So, okay, so in this, again, even in the simple version, you can say, so how do I, like if I know the spectrum and I want to get the Hamiltonian, what do I do? Well, okay, I sort of just have to compute, like I guess, make a guess about the Hamiltonian and compute the spectrum. But remember, we're dealing with an infinite temperature system. Therefore, kind of the naive way of doing this is to just diagonalize. Basically, you have to find all the eigenstates in your system, and therefore you have to diagonalize exponentially large matrix, which is hard. And you have to do it not once, but many times, because you compute a spectrum for your first guess of the Hamiltonian, but then you want to correct it, and so you have to like compute the spectrum for the corrected version of the Hamiltonian, and then again and again and again. So it's a hard problem. And one can show that actually, since the problem is intrinsically quantum, it's not surprising that just computing the spectrum would be very natural for the quantum algorithms. So in fact, one can check scaling that complexity, like even if we compute exactly, allowing arbitrarily long-ranged two-body interaction, only scales as n squared rather than exponential in terms of complexity. And so the idea that we basically suggest is to sort of combine this if we want to solve this inference problem, that okay, we will use quantum computers to compute the spectrum, but of course to adjust parameters of the Hamiltonian, we will use a classical computer. So from this perspective, it is a hybrid sort of algorithm which sort of uses kind of the problem that's natural for quantum computing, which is to compute the spectrum, does on a quantum hardware, but optimization is done on a classical hardware. And of course, this follows sort of like several earlier work on hybrid approaches, including some done here on sort of by Christian and collaborators on simulation, sort of using hybrid algorithms for simulations of the lattice gauge theory. Okay, but so this, some of you may have, this I found from giving this talk before, some of you may have a suspicion that, well, but is the problem of computing the spectrum at infinite temperature really difficult? Because naively, we're used to, okay, infinite temperature, it should be all kind of hydrodynamic. Well, instead of giving you technical answer, let me show you an example. Like, so let's say you it's just very simple, like 4 spins, and you wanted to do very simple classical calculation, so-called Landau-Lifshitz equation. Then for the spectrum, you would get this yellow line. We could try to improve this semi-classical approximation using the so-called truncated Wigner. It still gives us just broadens the single blob, but it does not really give us the true spectrum, which really sort of contains information about different eigenstates in the many-body system. And formally, one can show that the complexity of this problem is DQC1. Okay. So anyway, so we have kind of idea for a classical algorithm, but then of course you have to check, like will you be able, like even if you can simulate, will you be able to actually converge to the right value of the parameters? And so this was actually a very sort of challenging problem from the point of view of classical machine learning, and this is like Dries managed to overcome Dries all these challenges. So more or less the argument is, if we were to start with a completely random guess about the Hamiltonian and try to optimize and match the spectrum, actually we would never reach it, because the landscape is very rough. It's and you can think about it this way. So it consists of some discrete peaks, and so you sort of find parameters which match one of these peaks, and then the system is just stuck. It doesn't want to change parameters, because anytime like there is a beta minimum elsewhere, but at least locally it's a fairly deep local minimum. So therefore you will have to start with an educated guess. And then if we start with some simple examples, let's say so Dries took actual data on NMR spectra of molecules which are relevant to actually human biology. And so if when he ran clustering algorithms, he actually found that they sort of naturally fall into four clusters. And then actually just from this clustering, you realize that there is some chemical reason for this clustering. So for example, if you look at this type of spectra, which seem to have small number of peaks, which of course mean that we have many degeneracies, well, then these are all molecules which have this sort of methyl group. So you see that these sort of 3 kind of hydrogen atoms are really in the equivalent position, whereas the spectrum, which we would call most, so to us this would look closest to a chain, is exactly where we sort of corresponds to molecules. We have this benzene ring, and you have this sort of 4 hydrogens on this sort of like lined up on this benzene ring as on a chain. And so the idea that actually works is that one first has to do the clustering, and therefore know at least roughly the family of the kind of Hamiltonians that one needs to start with. And then if one starts with this sort of correct guess about the cluster, then one can converge rather efficiently in sort of tens of iterations. And of course, the kind of the most challenging part these days about doing anything with quantum computing is not suggesting an algorithm, but rather demonstrating that you can make it work on current NISQ devices. So here we were kind of fortunate to collaborate with the Maryland group. And so this is an example of the so-called zero-field NMR, which actually turns out to be particularly hard for sort of solutions based on the classical algorithms. I mean, they're not as popular as sort of large field NMRs, but actually it is kind of, there is a lot of appeal since they can usually be done much more cheaply. But by their nature, kind of NMR spectra, they have much more correlations, and that's why sort of why it's not really being used in practice. But okay, so basically, to cut the long story short, so this is the spectrum, right? Which this is a molecule, and what you can see here is the spectrum which was measured on in the 0 NMR by Dima Butker's group, and sort of the spectrum which was simulated using iron-based quantum computer. And this sort of required quite sort of a lot of investment on both theory and experiment, since the constraints came not only from the number of gates which one could apply, but also from the number of measurements. Because when we first sort of approached our colleagues and said, oh, you know, like it's a spectrum which consists these sharp features, so we would like you to make 4,000 measurements. They told us that, you know, even when they do 100, it's taking the entire weekend, and they're not willing to spend more time on that. So Kushal and Dries had to figure out sort of tricks based on compressed sensing, where you are really just sort of putting in information that you know that the spectrum will consist of discrete peaks, but you're not really making a guess about the actual Hamiltonian. So, okay, of course, this is just for demonstration purposes, but what kind of we can, like you can say this specific calculation for spins we can solve exactly, but this allows us to actually try to make some sort of scaling checks and understand. So we take problems which are currently sort of challenging. I mean, they're still doable with traditional algorithms, such like, and one of the most popular ones is the so-called spinach, but there is so much entanglement, the sort of basically coordination number of spins is large. So there is a lot of entanglement between the spins generated during the dynamics that it actually requires substantial computational times. And notice that here we're talking about systems not with thousands of sort of spins or qubits, but just, you know, 20 or 30. And now we can ask, okay, so what are the conditions for on our hardware in order to be able to solve these problems which are already sort of at the frontier of what can be done with the canonical methods. And there is an interesting combination here, because we're implementing spin dynamics using trotterization, right? So, you know, because we cannot just really make a Hamiltonian where we have this, you know, kind of specific interaction, Heisenberg SU2 symmetric interaction between different pairs of spins. We have to synthesize it using natural gates between these qubits. And this is achieved by doing trotter, by basically dividing evolution into small steps. And then to be accurate, you would like to have many steps. But on the other hand, if you have many steps, you have to do many qubit operations. And every qubit operation is imprecise. And therefore, you can find the optimal number of steps. And this optimal number of steps depends on what is infidelity of your gates. And so we can put in put in the numbers. And what we find is that basically, okay, currently infidelity is of the order of 10 to minus 2. But when one can have infidelity of 10 to minus 4, and when the number of operations will be of the order of 100,000, then we will reach sort of accuracy needed for NMR spectroscopy. And I want to emphasize, so this is very different from, say, this error correcting codes, right? There, people also use this number 10 to minus 4, but then the argument is beyond this number, they will be able to do good error correction. But in the case of NMR inference, in some sense, the problem is easier because NMR spectra have a natural line width. You don't want to compute spectrum better than, you know, than the intrinsic line width. You're not getting any new information. And that's why we just need to sort of reach these parameters, and then, you know, just without any error corrections, we can already do something that is quite promising for applications in biomedical sciences. Okay, so with this, let me conclude. So I tried to sort of tell you about some of the ideas that we have been developing for quantum simulations in the context which is perhaps more interesting to our physics community, and this is a Fermi Hubbard model, kind of the nature of doped Fermi Hubbard model, seeing sort of the emergence of pairing, and also using machine learning tools to analyze this many-body snapshot. And also, sort of, I think that there will be some very interesting questions we can address, and practical ones, by moving quantum simulations outside of the physics domain, say, but to problems which are intrinsically quantum, such as NMR. Thank you.
Thank you very much, Eugene, for the nice talk. So now it's time for questions. Please wait that the mic arrives to you so that the question is recorded. So, who wants to start?
Thank you for the great talk. I had a question about your last part. I mean, this notion of learning Hamiltonians by learning the corresponding coefficients. So in your case, it would be this kind of a spin model. So when we do Hamiltonian learning, we usually require much more information than simply measuring a spectrum. So to what extent is this actually unique, what you do here? I mean, that you really can uniquely reconstruct the Hamiltonian, and is there some sort of a quantitative error assessment that we have in the standard Hamiltonian learning context?
So, first of all, it's not just the spectrum, right? We also have matrix elements. It's a very specific operator. So, in particular, let's say that was one of the things I rushed over. Like if you look at the simulation of zero field NMR, the biggest discrepancy between theory, between simulation and experiment is, see in experiment there is no peak at j/2, whereas in the simulation there is. And the reason is there is actually a level difference with energy j/2, but there is a symmetry in the Hamiltonian, and which makes matrix element vanish. And that's why in actual NMR you don't see this peak. But of course, errors, even if you implement symmetric Hamiltonians, errors do not have to obey the symmetry, and that's why we actually see this extra peak. So, disclaimer number one, that it's actually we know not just the spectrum but also matrix elements. In terms of information, at least mathematically, the problem is overdefined because you can show that the number of basically the number of peaks the spectrum has exponential number of terms, right? Whereas the number of parameters that we have is scales only as a power law, right? As n squared. That's why we actually have more information than we need in principle to predict the Hamiltonian.
Can you also write down error bars for these things at the end?
So the error bars, like for a specific quantum.
For all of your couplings in your whole geometry. I mean, it's really quantitative, and then you assign accuracy.
It's an interesting question. So what we do, so it's something that, we're still working on. What it seems to, it actually depends on how many measurements you will allow me to measure, to do. Because if, first of all, we still have to do, it's a longer story, but more or less you can show that this optimization landscape is you can map it into some kind of free energy problem. And then if you do, it's actually like at least for some version, like Ising version, you can show there is an exact mapping. And if the number of measurements and is small, it's as if you are trying to find kind of free energy landscape, but then your temperature is very high, and therefore you are kind of moving everywhere. You don't see the kind of the bottoms of the potential. But when you reduce, when you increase the number of measurements, it's like you lower the temperature in this landscape, and you start going towards this minima. But the question whether whether it's so glassy that you will not be able to find a true minimum, you will be stuck in some metastable state. I think it also depends on how you formulate it, because remember I told you if I start with a random spin Hamiltonian, I know that I will never be able to find it, right? Because it's such a rough landscape. So I have to start sufficiently close. So far what we have seen is that nature is kind to you, like biological molecules seem to make fairly we only looked at small ones, like clusters which are close to each other. That's why I think your problem, we would have to define, what is your starting point, how well I can define. I think the biggest problem is not just, how well I can sort of zoom in onto my local minimum, if it is the correct minimum, but whether I will be stuck in a false minimum or not when I try to optimize, and that depends on how closely I start and what is the number of measurements that our experimental colleagues are willing to do. Does it answer your question?
Yeah. Good. More questions? Maybe I have one actually a bit on a more general perspective regarding the idea of using neural networks to identify phases of matter, like you have applied for the images in the experiments. So what's your take? So are we learning physics from these or not? Or in which scenarios, how one does?
Well, that's exactly why we wanted to get this sort of interpretable architecture, right? Because the first part you can say that was a bit of a black box, so neural networks tells you this is a good description experiment, this is not. But in this case, we can sort of really sort of understand what are the minimal features taken by the neural network, so that it can distinguish two theories. And in this case, we managed to, well, okay, it's really Annabelle, Cole, and Una. They managed to figure out that this starts with these 2x2 clusters. So you're starting with, like, you need at least four site correlator in order to start distinguishing, let's say, RVB from these string-like models.
Thank you.
Hi, Eugene. Thanks very much for this nice talk. I have a question actually regarding this part. So, as far as I understand, you compared, you let the machine decide sort of whether a snapshot is from one theory, another theory, or an experiment.
That was so this specific.
That, yeah,
before that, that was one of the methods. Yes.
Can you use this type of methods to, learn how or interpret how the machine discriminates between experiment and, the good theory, and maybe learn, what is not captured by the good theory?
In a sense, that's what we wanted to do, but then because the data we had available at that point was just Marcus's data, which did not have spin resolution. That's why this question of interpretability we did only on simulated theoretical data. Once they go through the upgrade, they'll give us images, like experimental images. We can do the same procedure, because, I mean, as a method works, you just have to feed it different kind of sources of data.
Any more questions? Okay, so if this is not the case, we thank Eugene once more for his talk.
Thank you.
And you are now all invited to enjoy some snacks and beverages outside and to keep the discussion with Eugene and everybody. So thank you for coming.